Morning, nerds. Morning. We're back at it. Squib it. We're going to continue working on section 2.5. We're not going to finish it today. We'll finish it tomorrow. That puts your 2.1 to 2.5 test on Thursday of next week. Because I'm going to, remember I told you I have addendum notes, stuff that I want to add to section 2.5? Since it's not on your upcoming assessment, I'm going to teach it to you Friday of next week because we have the weird bell schedule because of the pep rally. There's a pep rally next week on Friday between third and fourth period. So all of our class periods are a lot shorter. So that'd be the perfect day to teach you short notes and teach you stuff that you're not going to be assessed on this coming test. Next week is pep rally, is Spirit Week. Okay, so yes. Ah, geez, hold on. I'm just going to pause the video while I get all these questions out of the way. Yep. All right, so for this question, I mean, yesterday we kind of did something similar to it, right? We took this polynomial and we were supposed to find it in its linear factorization. That means find all of its solutions and write them all in x minus some number setup. And we got all the way down to here. So we were able to find these three real factors because this is where our graph crossed the x-axis. And we were able to double check that with the second table or graph or whatever it's called, second graph took us to the table. And these three factors multiply out to give you this cubic factor of our quadratic. We divided using long division, and it left us with this irreducible quadratic. Irreducible meaning it doesn't have real zeros, and even if they were real, they're also not pretty. Basically, this doesn't factor. Okay? It's irreducible. Regardless, it does have two solutions, set it equal to 0, boop, and solve. Ta-da, like that. That was an easy one, though. It was an easy one to solve because it said x squared and then a number. We could just set it equal to 0 and get x by itself. Unfortunately, that's not always the case. Sometimes when you do this long division, you get a full quadratic. It has all three terms, and yet it's irreducible. So what would happen if you got a quadratic that was irreducible that had all three terms? How would you solve? What if it doesn't factor, though? The quadratic formula is unfortunately how you would handle that. Don't write large. We were told that 1 minus 2i is one of the solutions of this fourth degree polynomial. That means there's another complex solution that wasn't said. But it must be true. This thing's complex conjugate, 1 minus 2i, is also a solution. Plus 2i, excuse me. So that is also a solution. What I taught you to do before was if you have complex conjugate solutions, it's best, I think it's best, to recreate the quadratic that produces them. That gets you an irreducible quadratic, but you would then be able to divide by that quadratic. So we know x is 1 plus or minus 2i. And to rebuild the quadratic, what we need to do is isolate the imaginary component so we can square it. Because squaring an imaginary always gives us a real. So we subtract a 1 from both sides. It doesn't matter that this says plus or minus because we're going to square it. And when you square a positive number, you get a positive number. When you square a negative number, you get a positive number. So we will square both sides, and we will no longer have anything imaginary. This is AP. I am going to hope that you know how to do x minus 1 times x minus 1. And we're trying not to take up a lot of space, and because the pattern is so easy to follow, again, we don't worry about the plus or minus. When you square this 2, what are you going to get? 4. When you square I, what do you get? Negative 1. So this says 4 times negative 1. So it would be great if you could go directly from squaring your imaginary numbers to a real number, a negative real number. That would be fantastic because that would be less work for you to write. Now you can just add this 4 to both sides, and you have an irreducible quadratic factor of your 4th degree polynomial. Yay! X squared minus 2x plus 5 is one of my factors. So when I do the long division, there won't be a remainder, because this is one of my factors. Time for long division. Just remember, one really important thing when you're doing long division of your polynomials. What are you always looking out for? You need your like terms to line up, which requires there to be no gaps. No gaps. X to the 4, 3. Oh, there's no x to the 3rd. This thing has a gap at x to the 3rd. So we're going to be dividing x squared minus 2x plus 5 into this polynomial, but we will have a 0x to the 3rd. No gap teeth smiles. Yeah, don't write too large. I always end up writing up and to the right. I don't know why. There we go. Our job is to make this x squared become a 4x to the 4th. What do I multiply by? I need a 4 and I need 2 more x's, so 4x squared. I'm going to put that way over here so that my like terms line up. We now take this 4x squared and we distribute it. 4x squared times x squared gives me 4x to the 4th. 4x squared times negative 2x gets me negative 8x squared. Negative 8x to the 3rd. Sorry. And 4x squared times 5 gives me positive 20x squared. And we are subtracting straight down. Just watch your double negatives. Remember, anytime you say minus negative, that actually means plus. So 4 minus 4, yeah, that's 0. 0 minus negative 8, that means plus. 0 plus 8. 8x to the 3rd. 17 minus 20, negative 3x squared. And let's drop down our next term. All right. Once again, try to make the fronts match. So we need this x squared to become an 8x to the 3rd. What do we need to make this happen? Just someone say it. 8x. I need an 8, and I need one more x, so plus 8x. Now we distribute that 8x to over here. 8x times x squared is 8x to the 3rd. 8x times negative 2x is negative 16x squared. And 8x times 5 is 40x. Subtracting straight down, just watch your double negatives. Minus negative means plus. 8 minus 8, 0. Negative 3 minus negative, plus. Okay, negative 3 plus 16 is 13x squared. 8x times 5 is 40. Wait, what am I talking about? Minus, sorry. 14 minus 40 is negative 26x. And lastly, drop down the plus, not minus, the plus 65. And I'm trying to make x squared become 13x squared. What do I have to multiply by? 13. And look what kind of magic happens when you multiply 13 across this thing. No, it's not magic. We were expecting no remainder. Remember, we said it was a factor. So, shouldn't be surprised by that result. All right, cool. We got a quadratic. We need to solve. Let's see if we can factor. Are there two numbers that multiply to 52 that add to 8? No, yeah, because 4 times 13 is 52. So no, there are no two numbers that multiply to 52 that add to 8. Crapola. I wonder how we're going to solve. Quadratic formula. You guys are about to get a rare treat. I am going to sing the quadratic formula song for you, but I will not be doing it on camera because I don't want evidence of such. Anyway, I sang 3 songs for you guys. Lucky you. No, well, 2 different ones, but I did sing 3 times. So, yes, I did. I did Row Row Your Boat twice. I did it first, then I did Pop Goes the Weasel, then I did it again. That's 3. Yes, you just weren't paying attention. Hey, how many times did I sing it? 3. You just weren't paying attention. Anyway, in case you didn't know, A is 4, B is 8, and C is 13. In case you didn't know. So x equals negative b, so negative 8, plus or minus root b squared, 64, minus 4 times a times c. That was supposed to be a 4, but for some reason I wrote a 3. I'm not really sure what happened to my brain there. All over 2a, but 2a is 8. Now I'm not going to lie. You're probably going to want to grab a calculator just to make sure you don't goof this part up here. But I've already done that. This number is negative 144 in here. (144) is a perfect square. So what is the square root of negative 144? 12i. Yep. So we have negative 8 plus or minus 12i over 8. When we write out our linear factorization, we actually have to have our complex numbers in standard form, which means we have to separate them into 2 different things. And standard form is a plus bi, which means I can't leave it as negative 8 plus 12i over 8. It can't be like that. It actually has to be separated. It's negative 8 over 8 plus or minus 12i over 8. I'm running out of space. Like that. And then you reduce. So what you get is negative 1 plus or minus 3 over 2i. Those are your 2 complex conjugate solutions. No, don't do 1.5, do 3 over 2. We were asked to find the linear factorization. All 4 solutions were complex. What does that tell you about this graph? This graph never touches the x-axis. Well, that was possible because it was an x to the 4th graph. X to the 4th graphs, their endings are going to point the same direction. So it's possible that the graph never touches the x-axis, and this one doesn't. Here is your linear factorization. Lots of brackets and parentheses. Bracket x minus. The first 0 we knew about was 1 minus 2i. And we said because of that one, the conjugate 1 plus 2i is also a solution. So x minus 1 plus 2i. We then found these 2. Told you write small. I told you write small. Fun in a bun. Look at that. We were given a 4th degree polynomial and 1 complex solution. From that knowledge alone, we were able to find all 4 complex solutions. Yes, Adi. Well, all solutions are going to be written as x minus something. So x minus negative 2, x minus 1, x minus 4. It's like transformations, inside opposite. Well, you need the parentheses because this is a single number. 1 minus 2i is a two-dimensional number. So it's x minus that number. Without the parentheses, if you didn't write the parentheses and you just wrote x minus 1 minus 2i with no parentheses, your answer is wrong. Okay? You have to keep your complex number in parentheses, or you have to distribute the minus sign. Yes? No, you're not allowed to write it as plus minus. No, you do have to write out all four if it says the linear factorization. You have any questions for me about that one? Sorry about the quadratic formula. It just is a necessary evil sometimes. Yeah, the quadratic formula is... Wow. You guys want to know something really cool? There is a secondary quadratic formula. It's completely different. Just another way of solving the quadratics. It still has a square root. It still has a plus or minus. The fraction is upside down, and the letters are reordered in different ways. And I didn't even know it existed until like a couple years ago. I don't even know it. No, you don't have to learn it. I don't know it. But it's really cool. Well, you know why you guys probably don't like the quadratic formula? You don't know why it's true. You've never seen where it comes from. Why is it a she? I feel like it's so powerful it has to be a guy. Got him. Look at all the women's mouths hit the floor. Ah, got him. Got him. Triggered. Trigger warning on this video, everybody. Yo, what's up? Oh, did she? Good for her. Good for her. She should. I will when the notes are over. Anyway, every polynomial function with real coefficients can be written as a product of linear factors, which we've been doing, and also irreducible quadratic factors with real coefficients. So what does that mean? That means if you were asked to factor a polynomial, if I didn't say write it in linear factorization, if I just said factor it, then you would never write an answer like this. This is linear factorization. No. What you would have done is you would have written an answer like, where do I have one where I could show you? Here. Not even like that. Crud. Why don't I have one for you guys? I did for last period. Man. Well, right here. For this question, both of these quadratics were irreducible quadratic factors. So if you were asked to factor a polynomial that had these 5 solutions, that factorization would actually just say x minus 1 times this purple thing times this blue thing. That's factored because these are irreducible. So if you're told to factor something into to linear factors and irreducible quadratics, don't break it into its imaginary solutions or complex solutions. Leave it factored, but ugly things that aren't going to factor nice just stay quadratic. The irreducible quadratic factors would yield the complex conjugate zeros. That doesn't mean every irreducible quadratic factor gets complex conjugate zeros, but that is where they will come from. Now, in this last example, we had a 4th degree polynomial and we found out it had no real solutions, right? This next box says odd degree polynomials, because they have in behavior of 1 up and 1 down, they're guaranteed to have at least one real solution because the endings point different directions, forever up, forever down. One of them will encounter the x-axis, at least one of them. Yay is right. We have a fifth degree polynomial. Guaranteed we have at least one real solution. What we will do is the same thing we did yesterday. We grab our calculator and we will graph it to hunt for possible real solutions that are pretty. Turn it on. Oops. No, I don't want to see that. I'm doing this. You're supposed to be doing this with me. Anyway, I already have it ready to rock and roll. It's typed up right there. Oh, he sent it to me over Remind. Joy. Okay. When my phone makes two noises like that, it means it's coming from a student.
So you ignore it?
I'm working. Oh, I would only ignore if it was coming from you. What she knows isn't true. Anyway, I'm going to go ahead and graph this thing because I'm hunting for possible real solutions. Graphola. Hold on. Quit. Zoom 6. There we go. I forgot to hit Zoom 6. It's thinking really hard about this. There's one. There's two. There's three. All right. It does have three real solutions. Now, here's what we don't know. Is there another wiggle up here somewhere? And it comes back down and then back up? Like, is the window just not large enough? I don't know. You could always make the window larger, more X's, more Y's, just to see if there are more solutions. But I'm going to go ahead and tell you there aren't more solutions. So what are our possible real solutions? Zoom. I'm just going to hit in and hit enter on the origin. So I just zoomed in closer to the origin. All right, we've got a negative number there, a positive one there, and a negative one. And another positive one there. We want to know what these numbers are, right? So what do we see as possible results? Give me a possible answer here. Negative 1.5, and this one's possible answer? Looks like close to 1.5 or something like that, right? So here's what I'm going to do. I'm going to go to my table. Second table, or second graph, I should say. I already have mine set up to go by 0.5s. If you don't remember how to do that, I'm just going to remind you, press plus, and then hit 0.5 and hit enter. And it'll change everything to 0.5s, okay? Anyway, negative 1.5 looked like it might be a solution. Crud. It's not. And neither is negative 1. So we know there's an answer between negative 1 and negative 1.5. How do I know there's an answer between them? Because my y values went from negative to positive. I guaranteed I crossed to the x-axis. And it looked like I might have one at 1.5. Clearly I don't. But there is one between 1 and 1.5. So then this one is one that we're probably going to be hunting for. If we had to take a stab at that one, what would we guess? No, 1 3/4 is way over here. Maybe 3/4. All right, so go to table. I'm going to scroll up to 0, and I'm going to do plus, and I'm going to do 0.75s. And did 0.75 give me an answer? It did not. All right, 0.75 didn't work. Next. How about something even better than that? What about 2/3? Holy crap, there it is. Or we could have just done second trace intersect. The reason why I didn't do second trace intersect was because I was concerned you would try to do that for all three. No. Because if you tried for all three, you would have gotten a really ugly answer for the other two. Here's the one that we know works perfectly though. X equals 2/3 is perfect. So what is the linear factor associated with x equals 2/3? X minus 2/3 will work, but the problem with x minus 2/3 is if I went ahead and distributed all that out, there's a very low likelihood I would end up with nice whole numbers. So there's nothing wrong with x equals or x minus 2/3. It's just that it's not going to result in this. So what do? 3x minus 2. You take this denominator and scoot it to the front, just like you would have done for the Lizzie method. And you'll find out that 3x minus 2 is a linear factor. We have one of the 5 factors. And the other two don't look like they're going to play nice. So we're going to go ahead and do long division with that. Five, four, three, two, one, none. We're not missing any teeth here. Okay, now, long division. I know that every time we've done long division, I've only dropped down one term at a time. And that is usually how that happens, but that's because after you do the whole subtraction, you usually have one thing there and you get to drop down one more. She's raised her hand twice now. It must mean I missed something. Yes, what's up? Yeah, it's definitely supposed to be -2. So we'll just ignore that. That would have messed up everything. Very good catch. Cool. Long division time. I need this 3x to become a 3x to the 5th. X to the 4th, yeah. X to the 4th, I like my like terms to line up, so I'm going to put that right here. I'm going to distribute that x to the 4th now. X to the 4th times 3x is going to give me 3x to the 5th. And x to the 4th times -2 is -2x to the 4th. Now, when I subtract straight down, I'm going to get, 0. So what I'm going to do is bring down 2 objects because I'm trying to divide with an object of size 2. So I'm going to bring down 6x to the 3rd and -4x. So I'm trying to make a 3x become a become a 6x to the 3rd. Thanks. I need this 3x to become a 6x to the 3rd. 2x will do it. It's 2x squared, right? Yeah. Earlier, someone said, why is there a gap there? And it's because I want my like terms to line up. That's the only reason why. All right, so I'm going to take this 2x to the 2nd. I'm going to distribute it. It's going to give me 6x to the 3rd and a -4x squared. And golly gee, it happened again. No, definitely not kidding. So we will be forced to drop down 2 objects again. And we will get -24x plus 16. And I need to make a 3x become a -24x. A -8 will make it happen. And we shouldn't be surprised by the fact that there's not going to be a remainder because we specifically said that 3x minus 2 was a factor. So we know that we didn't screw anything up. We're good here. But what did we get? We got this 4th degree polynomial. That's what we got. X to the 4th plus 2x squared minus 8. You know what? I have an idea. I'm gonna push my note paper up so we can get all the way down to the bottom of the page. I just wanna show you something real quick. Skirt. Let's go all the way to the bottom. Hey, I would like you to tell me how to factor x squared plus 2x minus 8. How does that factor? X plus 4, yeah. And x minus 2. So why did I bother showing you x squared plus 2x minus 8? Well, first of all, what I'd like you to see is this. You see how here my factors, the degree on the x is the same as the degree here? And did you notice that if I multiply these two things, I'll get this degree? Literally, these have a degree that is half of this, and it's the same degree as this. Ultimately, the pattern works like this. If the middle degree is half of the first degree, it factors the exact same way. But instead of x plus 4 and x minus 2, it's x squared. Because look, x to the 4th minus 2x squared plus 4x squared minus 8. It didn't ask me to find all the solutions, but I could. What are the solutions here? Plus or minus 2i. What are the results here? Plus or minus the square root of 2. It didn't ask us to do this, but this gives me x equals plus or minus 2i. This gives me x equals plus or minus the square root of 2. So the reason why 1.5 didn't work is because those two results are actually at positive and negative square root of 2, which is right around the 1.41 mark. That means both of these are irreducible quadratics, and our final result is f of x equals 3x minus 2, and then our two irreducible quadratics. If I was asked to put it in linear factorization, I would have to use all 5, and I would have to use both of these, but that's not what it said, so we're finished here. But something really interesting just occurred. That was never in a box anywhere, meaning one of these boxes. The reason why complex answers come in conjugate pairs is because at some point in time you're taking the square root of a squared x, which creates a plus or a minus, and that's what makes it the conjugate. But all irreducible quadratics will solve and have a plus or minus in them, won't they? So not only do complex answers have to come in conjugate pairs, a very specific type of irrational solution must come in conjugate pairs as well. If f of x has x equals a plus b root c as a solution, then the conjugate x equals a minus b root c is a solution as well. So yes, all complex results come in conjugate pairs, and specifically irrational forms or irrational zeros of this form also come in conjugate pairs. Mr. M, ours didn't look like that. Actually, it did. This is 0 plus 1 root 2. So yes, it did look like that. It was just very, very simplified. That's not to say that every I don't want you to think that every irrational answer comes in a conjugate pair. They have to be of a very specific format, because there are a lot of irrational numbers that are not square roots of things, like pi or e and things like that. Okay? I think that's a good stopping point, nerds.